Hi, welcome to another chem video. Today we're going to talk about entropy, which is our last topic of the chapter. So today we're going to talk about what entropy is and how to apply that to chemical reactions. We're going to start with the do now and Le Chatelier's principle, finish out our notes, and then there's a few practice questions after this. Starting with our do now, so we have an equilibrium system, nitrogen gas plus oxygen gas plus energy becoming nitrogen monoxide. Reminder, when energy is on our reactant side, this is an endothermic reaction, it's absorbing energy. Let's take a look at the question, which changes will result in a decrease in the amount of nitrogen monoxide formed? I'm going to go over each of the answer choices and why or why not it's the answer, but let's look at number one. So decreasing the pressure. So again, pressure only affects gases. Our equilibrium does have gas on either side of our equilibrium arrow. We have 1 plus 1 for 2 moles of gas on our reactant side. We have 2 moles of gas on our product side. So we have 2 moles of gas on either side of our equation, which means pressure will have no effect or cause no shift in our equilibrium. Option number 2, decreasing the concentration of nitrogen. So if we decrease the concentration of nitrogen, our equilibrium is going to shift in order to replace it or start producing nitrogen again. So we're going to see a left shift, or we're going to favor the reverse reaction. Number 3, if we increase the concentration of oxygen, we're going to experience a right shift, or favoring the forward reaction, because we're going to want to use up our excess oxygen. So we're going to experience a forward favored reaction. If we increase the temperature or the energy of the system, same thing, we're going to use up that excess energy and favor the forward reaction. So let's see, which of these decreases the amount of NO? So to decrease the amount of nitrogen oxide formed, we need to treat nitrogen oxide as a reactant. The only option that does that is number 2. When we decrease N2, we favor the reverse reaction, which means we are using up nitrogen oxide to produce nitrogen and oxygen. Entropy is a term that means randomness or disorder. It is a measure of how chaotic a system is. A system that has greater disorder or is more chaotic has greater entropy. For example, this image has less entropy than this image. This is ordered and completely put into color order. This is chaotic and randomly thrown around paper clips. Therefore, this has the greater disorder or greater entropy of the two photos. So when we're talking about entropy or disorder, we're really just talking about a system that is less organized. In nature or real life, systems are going to head towards higher entropy, so that means more disorder, and lower energy. This tends to favor exothermic reactions. More exothermic reactions are spontaneous, meaning they'll just happen without someone forcing it to happen. But everything in nature tends towards higher entropy, so more disorder, and lower energy. So make sure you keep this in mind. This is a highlighted statement right here. The degree of disorder in a chemical reaction is going to depend on the state of matter that we're looking at. So think back to your particle diagrams from way back in September and the way your solids, liquids, and gases look. Gas particles have random motion, they're spread out, there's more disorder to a gas particle diagram than there is a solid. So gases are our highest entropy state. Liquid particles have some movement but are more restricted, so they have a little bit less entropy than gases. Solid particles vibrate in place but have significantly less movement than both gases and liquids, and thus have our lowest entropy state of our states of matter. One other thing to address are solutions. Solutions have an entropy somewhere between liquid and gases. They have more entropy than pure liquid because there are particles in solution. Our solvent particles are separated from our solvent particles. So there's a little bit more chaos in there compared to a pure liquid. But from least to greatest entropy, solids have the least entropy. Liquids have slightly more entropy, solutions have a little bit more entropy, and gases have our highest entropy. Again, this is a must know right here. So entropy in chemical reactions. So if you have a solid turning into a gas, there is going to be an increase in entropy because you're going from a solid where your particles are pretty close together in an ordered fashion to a gas where you have more spread out chaotic particles. You can also look at chemical reactions where gases are both on the reactant side and the product side, just like the example we're about to look at. But if the number of moles of gas increases in a chemical reaction, then the entropy is also going to increase for the chemical reaction. For example, if we have dinitrogen tetraoxide producing 2 moles of nitrogen dioxide, there are 2 moles of gas on our product side compared to only 1 mole of gas on our reactant side, meaning this reaction does cause an increase of entropy because we're producing more moles of gas as our product. Now what I would like for you to do is pause the video and copy this table into your notebook. So we're going to take a look at each of these reactions, what the change in entropy overall is for the chemical reaction, and the reasoning behind why I'm saying it is that change in entropy. So looking at this first reaction, we have aqueous silver ions plus aqueous chlorine ions making solid silver chloride. So we're going from an aqueous state where our particles have some movement in liquid to a solid state where our particles are close together and ordered. Therefore, we have a decrease in entropy. And like I just said, we're going from an aqueous state to a solid state. And we have 2 moles of substance, right? 1 mole plus 1 mole is 2 moles to only 1 single mole of substance. Therefore, we see an overall decrease in amount, as well as we're going from aqueous to solid state. In our second example, we have liquid water becoming hydrogen gas and oxygen gas. We're going from a liquid to gas state. Gases have our highest entropy state. Therefore, there's an overall increase in entropy. Like I said, we're going from liquid to gas. Gases have spread out particles, more chaotic order. We're also going from, this should say 2 moles of water to 3 moles of gas. So we also have more moles of substance on our product side in addition to it being 3 moles of gas instead of 2 moles of liquid. Let's look at our next equation. So we have a combustion reaction here. We have gases on either side, but on our reactant side we have 4 moles of gas. On our product side we have 1 plus 1, which is 2 moles of gas. Therefore, we see a decrease in entropy. We have a reaction here where we have 4 moles of gas turning into 2 moles of gas. We have less gas particles overall, therefore a decrease in entropy. And last equation, we have calcium carbonate becoming calcium oxide and carbon dioxide. So we have a solid changing into a solid plus a gas. Our products contain a gas, which again have our highest entropy state, therefore overall we see an increase. In addition to a solid becoming a gas, we also have 1 mole of substance on our reactant side becoming 2 moles of substance on our product side. So we have more particles, and it includes a gas, which has a high entropy state. If you have any questions, as always, feel free to email me. I hope you have a good day.